Part I: Foundations of Data Systems. The first 4 chapters go through the fundamental ideas that apply to all data systems, whether running on a single machine or distributed across a cluster of machines. Chapter 1 introduces the terminology and approach that we're going to use throughout this book. It examines what we actually mean by words like reliability, scalability, and maintainability, and how we can try to achieve these goals. Chapter 2 compares several different data models and query languages, the most visible distinguishing factor between databases. From a developer's point of view, we will see how different models are appropriate to different situations. Chapter 3 turns to the internals of storage engines and looks at how databases lay out data on disk. Different storage engines are optimized for different workloads, and choosing the right one can have a huge effect on performance. Chapter 4 compares various formats for data encoding serialization and especially examines how they fare in an environment where application requirements change and schemas need to adapt over time. Later, Part II will turn to the particular issues of distributed data systems. Chapter 1: Reliable, Scalable, and Maintainable Applications. The Internet was done so well that most people think of it as a natural resource like the Pacific Ocean, rather than something that was man-made. When was the last time a technology with a scale like that was so error-free? Alan Kay, in interview with Dr. Dobbs Journal 2012. Many applications today are data-intensive, as opposed to compute-intensive. Raw CPU power is rarely a limiting factor for these applications. Bigger problems are usually the amount of data, the complexity of data, and the speed at which it is changing. A data-intensive application is typically built from standard building blocks that provide commonly needed functionality. For example, many applications need to store data so that they, or another application, can find it again later. Databases, remember the result of an expensive operation, to speed up reads caches, allow users to search data by keyword or filter it in various ways. Search indexes, send a message to another process, to be handled asynchronously. Stream processing, periodically crunch a large amount of accumulated data. Batch processing. If that sounds painfully obvious, that's just because these data systems are such a successful abstraction. We use them all the time without thinking too much. When building an application, most engineers wouldn't dream of writing a new data storage engine from scratch, because databases are a perfectly good tool for the job. But reality is not that simple. There are many database systems with different characteristics, because different applications have different requirements. There are various approaches to caching, several ways of building search indexes, and so on. When building an application, we still need to figure out which tools and which approaches are the most appropriate for the task at hand. And it can be hard to combine tools when you need to do something that a single tool cannot do alone. This book is a journey through both the principles and the practicalities of data systems, and how you can use them to build data-intensive applications. We will explore what different tools have in common, what distinguishes them, and how they achieve their characteristics. In this chapter, we will start by exploring the fundamentals of what we are trying to achieve: reliable, scalable, and maintainable data systems. We'll clarify what those things mean, outline some ways of thinking about them, and go over the basics that we will need for later chapters. In the following chapters, we will continue layer by layer, looking at different design decisions that need to be considered when working on a data-intensive application. Thinking about data systems. We typically think of databases, queues, caches, etc. as being very different categories of tools. Although a database and a message queue have some superficial similarity, both store data for some time. They have very different access patterns, which means different performance characteristics, and thus very different implementations. So why should we lump them all together under an umbrella term like data systems? Many new tools for data storage and processing have emerged in recent years. They are optimized for a variety of different use cases, and they no longer neatly fit into traditional categories. For example, there are data stores that are also used as message queues, RDS, and there are message queues with database-like durability guarantees. Apache Kafka. The boundaries between the categories are becoming blurred. Secondly, increasingly many applications now have such demanding or wide-ranging requirements that a single tool can no longer meet all of its data processing and storage needs. Instead, the work is broken down into tasks that can be performed efficiently on a single tool, and those different tools are stitched together using application code. For example, if you have an application-managed caching layer using Memcached or similar, or a full-text search server such as Elasticsearch or Solr separate from your main database, It is normally the application code's responsibility to keep those caches and indexes in sync with the main database. Figure 1-1 gives a glimpse of what this may look like. We will go into detail in later chapters. Figure 1-1. One possible architecture for a data system that combines several components. When you combine several tools in order to provide a service, the services interface, or application programming interface API usually hides those implementation details from clients. Now you have essentially created a new, special-purpose data system from smaller, general-purpose components. Your composite data system may provide certain guarantees, for example that the cache will be correctly invalidated or updated on write so that outside clients see consistent results. You are now not only an application developer, but also a data system designer. If you are designing a data system or service, a lot of tricky questions arise. How do you ensure that the data remains correct and complete, even when things go wrong internally? How do you provide consistently good performance to clients, even when parts of your system are degraded? How do you scale to handle an increase in load? What does a good API for the service look like? There are many factors that may influence the design of a data system, including the skills and experience of the people involved, legacy system dependencies, the timescale for delivery, your organization's tolerance of different kinds of risk, regulatory constraints, etc. Those factors depend very much on the situation. In this book, we focus on 3 concerns that are important in most software systems. Reliability: the system should continue to work correctly, performing the correct function at the desired level of performance even in the face of adversity, hardware or software faults, and even human error. See reliability on page 6. Scalability: as the system grows in data volume, traffic volume, or complexity, there should be reasonable ways of dealing with that growth. See scalability on page 10. Maintainability: over time, many different people will work on the system engineering and operations, both maintaining current behavior and adapting the system to new use cases, and they should all be able to work on it productively. See maintainability on page 18. These words are often cast around without a clear understanding of what they mean. In the interest of thoughtful engineering, we will spend the rest of this chapter exploring ways of thinking about reliability, scalability, and maintainability. Then, in the following chapters, we will look at various techniques, architectures, and algorithms that are used in order to achieve those goals. Reliability. Everybody has an intuitive idea of what it means for something to be reliable or unreliable. For software, typical expectations include: the application performs the function that the user expected. It can tolerate the user making mistakes or using the software in unexpected ways. Its performance is good enough for the required use case, under the expected load and data volume. The system prevents any unauthorized access and abuse. If all those things together mean working correctly, then we can understand reliability as meaning, roughly, continuing to work correctly, even when things go wrong. The things that can go wrong are called faults, and systems that anticipate faults and can cope with them are called fault-tolerant or resilient. The former term is slightly misleading. It suggests that we could make a system tolerant of every possible kind of fault, which in reality is not feasible. If the entire planet Earth and all servers on it were swallowed by a black hole, tolerance of that fault would require web hosting in space. Good luck getting that budget item approved. So it only makes sense to talk about tolerating certain types of faults. Note that a fault is not the same as a failure. A fault is usually defined as one component of the system deviating from its spec, whereas a failure is when the system as a whole stops providing the required service to the user. It is impossible to reduce the probability of a fault to 0, therefore it is usually best to design fault tolerance mechanisms that prevent faults from causing failures. In this book we cover several techniques for building reliable systems from unreliable parts. Counterintuitively, in such fault-tolerant systems, it can make sense to increase the rate of faults by triggering them deliberately, for example, by randomly killing individual processes without warning. Many critical bugs are actually due to poor error handling. By deliberately inducing faults, you ensure that the fault tolerance machinery is continually exercised and tested, which can increase your confidence that faults will be handled correctly when they occur naturally. The Netflix Chaos Monkey is an example of this approach. Although we generally prefer tolerating faults over preventing faults, there are cases where prevention is better than cure, for example because no cure exists. This is the case with security matters. For example, If an attacker has compromised a system and gained access to sensitive data, that event cannot be undone. However, this book mostly deals with the kinds of faults that can be cured, as described in the following sections.